Thanks very much. All right, I'm Thomas Pan, organizer of the meetup. As usual, before we start the meetup, do we have anyone want to make any announcement? Anyone?
Hey, can we get everybody to grab a seat, please?
Yeah, can we everyone find a seat, please? And anyone want to make any announcement? Anyone? Okay.
On behalf of Walmart Labs, we are hiring, so that's an announcement.
Anyone else want to make an announcement? Right? No? Okay. All right. Hey, everybody, find a seat, please. We will start a meetup soon. And the person earlier made announcement is tonight's speaker, Ayon, who is the manager of Walmart Lab. So without ado, I just hand over the microphone to him.
Good evening, everyone. Welcome to Walmart Labs. And thanks, Thomas, for letting us host the event. So today we'll talk about our path for the past few months towards using eventual consistency for our large-scale web services. So we'll talk about how we achieve that with open source tools, open source packages like Kafka, SolrCloud, Hadoop, Avro, and so on. So at Walmart Labs, we are building the Walmart global e-commerce from the very ground up, literally, with data centers, hardware, platform software, virtualization, more platform software, and then services, front end. The entire thing is being built from the ground up. As part of the data foundation team, in the data foundation team, we build, manage, and provide tools for all OLTP transactions in this new platform. So I specifically mentioned OLTP because we are strictly focused on all the transactional fetch, save, data that goes in to serve the website. All the analytical tools, those pipeline is being handled by a different team, so that's not within the data foundation team. So in large-scale e-commerce, what are the typical problems that we face? Well, our customers love to shop online 24/7, and we love them for that. That also creates a little bit of problems for us in the back-end systems. We need to scale to those numbers and keep them happy all the time. When our online shoppers are not happy, they get slow response times, long wait times, and something not working, technical difficulties, they go away with bad taste in their mouth, and then it's very hard to get them back. It takes a long time for them to come back. Other thing we do is the number of reads, number of gets and fetches are many orders of magnitude more than the writes that we do. 100,000, hundreds of thousands, or 10,000 times more than reads. And those reads have to be very, very fast. And some studies have even put numbers around the milliseconds you have to wait for websites. So they've put cents to milliseconds in page loads, and that's why you have optimizations at various levels on these e-commerce websites, starting from the front end, load balancers, back end search engines, everywhere. Every millisecond counts. The other thing is scaling up only takes you so far. You buy bigger machines, bigger database machines, and it takes you only so far before it falls over, and then the performance gain for the high amount of money that you pay for the next level is exponential. Other things we have experienced here is you can't really do analytical queries on large-scale, real-time OLTP systems. Do not run full table scans and analytical queries every hour to figure out how many orders you received. It hurts the databases and backends a lot. No full table scans. And again, if you are used to building small websites, smaller scale applications, they work just fine on the LAMP stack. So you can start off with MySQL, and as you grow, even your search pages are being served by database queries. That works fine at small scale. Once you grow big, you add more and more indexes to your columns, more and more column indexes, and that'll keep slowing down your writes. And it is a very common observation, I think. So with the new platform and data foundation, we have taken an approach that kind of looks like this. I'll explain what's happening. On the very left-hand side, these are individual web services, and we have our team has a package called Forklift, which we're working towards making open source in the next year very soon. But that library actually takes your data object, business data object, and it will persist it to multiple data stores. It will send it to the database. It will keep the immediately consistent cache coherent with the database. And it'll also do read repairs. If it doesn't find the cache, we'll go to the database, fetch it, we do read repairs. And then, depending on whether our client takes advantage of the eventually consistent pipeline, if they do, there is a replication of the object that gets serialized into a message bus, and there are plugin-based consumers that write it to various other data stores. Now, each of these boxes are different web services, and they use they pick and choose the components of this architecture. Not everyone uses every piece. And what we'll focus today on is on this eventually consistent part. And here, there are other services who are more eventually consistent data tolerant. They follow a different path. They write to the message bus, send it to this eventually consistent stores, HDFS, other cache, search, and then they get their data directly from search engine. So when we start to talk about very large scale, first thing we have to do is look at scale out. I'm pretty sure everyone's familiar with scale out terminology. So when you try to scale out, you get no choice, you have to partition. So there's really no way around Brewer's cap theorem. So you have to partition, all your data stores are partitioned. There's not much of a choice there. Now given the first point, what I said was our customers love to shop all the time. They don't like the site being down. So availability is critical. It needs to always be available. So what gives? We have to choose these two. We have, in order to have availability, we have to choose eventual consistency. For some systems, like cart, checkout, or transactions like payment systems, they have to be immediately consistent, which they take availability, they sacrifice a little bit of availability. They'll say your submission of order takes a little bit more time than, let's say, bringing up a search page. So in those systems, they do A and P. Now, when we talk about eventual consistency in machine terms, it's very important to define eventual to the stakeholders. And this is a lesson we've learned. When engineers talk about eventual consistency and go to a business person and say, hey, we're going to serve all your pages from this eventual consistent data store, and they will just say, whoa, wait, what? No, I can't take eventually consistent data. I don't like stale data. But then you really have to quantify what are you talking about. And when you say it's a few milliseconds to a second or 15 seconds, in the worst case scenario, 1 minute beyond that, we'll call it not ready for your service consumption. When you explain that, it becomes much more palatable, and that's when you start to go in that direction. I'll show you some examples. Those are very familiar. Eventually consistent data store use case. These are snapshots from our Walmart site. You see the recommendation module over there. There's a product and a bunch of recommendations. Given that product, these are other products you might also like. The information presented here can tolerate a little bit of delay. So even if a price gets updated while this module is being served, there is really no add to cart button. You're not really making a buying choice. So you have to go into the detail page and get the latest price and then make the buying decision. So it's not really false advertising. It might be stale data. So when you go in there, so that's one. So you're, from the backend's perspective, this module gets that many IDs and it has to get all of these information in one shot and as fast as possible. And waiting for every object's most consistent, immediately consistent value will take a long time. So you don't want that loading and people will browse away from this page. Similarly for a search page. These are most item description, title, image, attributes, ship methods. These are really not changing by the millisecond, so you can tolerate some potential. So this is an example of typical data flow into eventual consistent data stores. If you, let's talk about the immediate consistent data store part. I see web service client, let's say this is a checkout page or item page which needs to show the immediately consistent data store. It goes to our orchestration service, which in turn calls other resource tiers, which are backed by, remember that diagram where the left-hand side it was coherent cache and with a database, with a sharded database. This goes in and fetches the most immediate. This side is designed for immediate consistency, and for a given item, it will fetch the most recent data for all of the different parts. And these resource tiers, let's say, item description, availability, ship price, ship methods, or item price, all of these are different. They get feed from a feeder which has the most recent information, and this orchestrated service provides that. Now, if it didn't have this and the use cases that we mentioned, recommendation service, search engine, if those guys were to come here and ask for 32 items or 64 items or many number of items to this goes in here and tries to fetch all of the information from these resource tiers for every item. Now then we have an availability problem. Then there's network, there is scaling these tiers, this particular cache technology, the database sharding, all of that gets loaded in a multiplicative manner. So all of a sudden, if search page decides we want to do 64 items per page, you have to scale all of this in a multiplicative manner. Enter the EC web client, web service clients. We say, hey, let's fetch it from somewhere else, an EC store. How do we feed an EC store? So we need to figure out how do we put the data in there. So here we have an event-driven updater. This is a logic that could listen from various, it could be a cron job, it could be event-driven, it could be any business event-driven updater. So let's say you have a trigger that says if a particular product goes out of stock, I need to update everything and get the latest information and send it over. Or if something gets price changed, then it doesn't have to listen to every sale that happens but significant events. So this updating event is much less frequent than all of these calls. So it gets a snapshot of this product from these guys, and then it takes that object, serializes that, puts it into a messaging service, and here we have different kinds of consumers. One consumer is writing to Hadoop, one consumer is writing to Solr. What happens to the data in Hadoop? Recommendation service, which could be a different team in the organization, they focus on the large amount of data, their algorithms, data mining, recommendation systems. They run their jobs and they pull the results. And this could also be, say, another team which does search relevance. They pull all of these bad jobs, they run their bad jobs, pull that information out, and saves that into their own data store. And that could be anything. It could be Oracle, it could be HBase, it could be Couchbase, anything. So they have their mined information, but this is kind of batch. Then they need to serve the recommendation module or the search relevance, the relevant search page on the site. So what they do is they go back, let's say in the real-time call, they get this particular item ID. They go to their data stores where they save the results of their algorithms. They find these 20 product IDs. Now they have the product IDs, but they would like to get a much more recent version of the products to show the item page. The image might have been updated in the past hour, hour and a half since the batch job run, the item price, more reviews, and so on. So they would like to get a more recent version, but then it doesn't have to be the absolute recent version. So they go ahead and send this read request to SolrCloud. And this data was fed in through here. So the call comes from the EC web service client and the orchestrated service. It says, oh, you are one of the use cases who can tolerate this eventually consistent data. I'm going to send you a request because you also are requesting for 20 items or 32 items or many items, which I don't want to tax these guys, and you're okay. We're going to fetch all of them together using a single search query, and it responds in sub 50 or sub 100 milliseconds. So how do we go about doing that? What were our challenges, practical challenges? Choose a messaging system. We chose Kafka, and it was already being used in various other teams, and it's supported by our Big Cloud data team. Next challenge are virtualization. There are various different experiences building search engine on virtualized computes. Everywhere I've spoken to, everyone eventually moves to a dedicated tenancy. So if you are using AWS or Rackspace or internal, you want to make sure that you get stable computes. You don't get resource contention with other use cases. Because a search engine really depends on in-memory indexes. You want that to be stable. You don't. So if your use case really takes off, you will eventually move to dedicated hardware or dedicated tenancy on the virtualized. We started with big dedicated bare metal hardware because of the timing of acquiring certain resources, and also we wanted to eliminate one because since we were doing the entire stack from scratch, we wanted to eliminate some uncertainties. But virtualization also requires complete lifecycle management, which we are getting there, but isn't there yet. We had to choose the serialization format, and after much discussions, we chose to go with Avro because it's picking up in terms of, well, schema plus data, compression. You'll see even Oracle's NoSQL, they're using Avro, and they've created some Avro catalog. So Avro is really coming out ahead of other serialization format sequence files and custom zipped files. Then you have come across the problem of taking your hierarchical business object and converting it into a flat object, because search engines really have denormalized data schemas. So how do you flatten this object so that it's still searchable in a generic way? There are a couple of ways we said we'll do a dot separated path name, but then you run into arrays, problem of arrays, and eventually we ended up with, we still have the facility of automatically flattening out the object, but then we have provided the plugin mechanism in the consumers where the application itself can do custom logic and pull out their attributes from however deep and put them into certain fields so that they're searchable, because it's very hard to satisfy flattening for all kinds of use cases which we have never seen. If you are familiar with Elasticsearch, it takes the entire JSON document, hierarchical, and puts them in there, and you probably wouldn't have this problem. We have not used it in this particular scenario, and I can't say what trouble you'll run into, so you'll have no problem. If you're already using something like HBase or Cassandra or some other role-based stores, your schema might already be flattened. Your attributes are all denormalized, so then you have easier. For Solr people, we have to deal with schema.xml, and I'm going to assume that quite a few of you are familiar with Solr schema. So we did schema.xml a certain feature of Solr, and then plugin-based flattening. So just a quick slide about SolrCloud, so web app wrapper around Lucene search engine, search library, and then SolrCloud is the distributed version of where a bunch of Solr nodes use Zookeeper to talk to each other and give you a cloud. We are not really going to get deep into SolrCloud because that's a completely separate topic. And there are lot better presentations online, resources and books and so on. So what we did with Solr's schema.xml is we had a choice of either having every application team create their own schema.xml from scratch and maintain it, or we could leverage dynamic fields. If we chose the first one, the teams would have to ramp up on what schema.xml, what does it mean to have indexed, stored, indexed and stored, multi-valued, and so on and so forth. So they would have to have a huge learning curve even before getting started. So and then if they changed anything in schema.xml, everything has to be reindexed. The entire corpus has to be reindexed. So to avoid that problem, we created this approach where using the dynamic field feature, we created a convention. If your field comes into the document as with these prefixes, we already know what you're thinking. And then this will get you kickstarted, and after that, you can go ahead, you own the schema.xml anyway. If you wanted to add any more features into your schema.xml, you can do that. So that's up to the team. One disadvantage of using this approach is that this section can grow pretty long of every different data type with every combination. So we picked a small enough set and permutations that our first customer would be satisfied with. So we send the document through Avro object, through Kafka, going into serialize and getting into Solr. We put in all the documents, and we said, let's test this thing out. We've got pretty big machines with lots of physical, large amounts of memory. See where we can take it. So we said no writes. Our queries had no scoring, sorting, or faceting. All the documents, all the queries that we're sending, all the documents ended up in the document cache. So the hit ratio was 100%. And where did we get? We initially got to, every query was sub-millisecond, 0.3, 0.2. 95th percentile was 0.3. 99th was around 0.5 milliseconds. And this graph shows per box 5-minute refresh rate per second. It went up to 2,000 actually. After I took the snapshot, we also pushed the machine up to almost 7,000 queries per second on a single box. But this is unrealistic. So initial Solr settings. See over here we have 99.6% physical memory usage, and we use the settings that it came with. No tuning yet. Then we got worse. Reality hit. We started our updates, and our 95th percentile time started to hundreds of milliseconds, and queries per second started falling off a cliff, even though the document hit ratio is almost close to 100%. So what happened? We made a few mistakes, and we're going to fix them. First thing, tune the parameters. These parameters are, I would say, there are a couple of sets online available in the community, and depending on the size of your boxes, you'll get a right set. And we did a lot of tuning and trial and error, and with help from some experts, we came to a set of parameters. More naive mistakes. First one you can make is Zookeeper in the same Solr machine. We did not experience this because from the very beginning, we had our Zookeeper nodes on our separate VMs. The biggest mistake we had was we were doing database file one doc per update, post, and commit. So you know how you database go, you write, begin transaction, do your update, do your write, and then commit. That is not for a search engine. Don't commit after every update. Solr commit is very different from how a database commits. And one thing that you'll immediately come to experience is to on-index searches. What happens is every time you issue a Solr commit, it will open a new index searcher, and that index searcher will start getting warmed up in the background. So if your warm-up takes 30 seconds and you're committing frequently, you have a whole stack of index searchers that are in memory and getting warmed up. So your query performance will go down tremendously. So lesson learned, batch as many docs as possible. Your application can tolerate in a single update post. And we chose to batch docs every second. For a consumer, it's going to post to Solr every second. So regardless of how much updates are coming to Kafka, for in a single second, it could be 100, 200, 500, 800, it would still make one post. So the batch size becomes big. It's not a bad thing. So then you have your soft commit, auto soft commit settings on the server, and the hard commits also on the Solr side. So you don't have to change your consumers to, don't want your clients to be issuing commits on the Solr side. And then we had some IO contention, log level contention. It was too high, we were debugging, so it was blocking on the writer. That was an easy fix. You really have to pay a good attention to your Zookeeper cluster. Zookeeper, best number is 5. Anyone who has used Zookeeper will say that. We have more number of nodes means slower writes, fewer nodes if it's 3. Well, first you have to pick odd number of nodes because your quorum is n by 2 plus 1. So if you have 3 nodes, quorum is 2. You can only tolerate 1 node failure. If you're 5, you can tolerate up to 2 node failures. If you are 7 and 9 and you go up, your write speeds go down because it'll take that long to get quorum. So in order for us to get 9 nodes, we actually deployed 3 nodes each in 3 different clouds, the virtualized clouds. So even if one cloud entirely went down, we still have 6 nodes, we could still get 5 to respond. That works. The other thing is, yeah, again, I couldn't stress it enough. Pay very good attention to your Zookeeper availability, as SolrCloud will only function for a little while. It does function for a little while. Serving queries, writes will stop, but your reads will work because your clients are talking directly to the nodes, and it doesn't really need to know who the shard leader is. It can send randomly to the previously cached information, other nodes it will send those to. So it will function for a little while, but it will not function for, it will go down pretty hard. And then Cloud Solr Server is a smart SolrJ client, which first talks to the Zookeeper and gets the Solr nodes, and then it fires query to the Solr nodes, just caches that information and goes from there. So the clients, if you have multiple different use cases who are talking to your Solr nodes directly, they rely on Zookeeper to talk to Solr. So it's an important piece. Disaster recovery. SolrCloud is CP model. It was a design choice because the choice was made because if a search engine returns inconsistent results as you shard and make more replicas and you're firing queries, you're getting 25 items once and then 27 and right next time 21, it gives you a bad impression of the search engine. So they really wanted to be consistent and partition tolerant, which means that every write has to be written to every node before it responds, which means that writes will be slow. It's an accepted fact, which is why you cannot do across data center SolrCloud. Do not do across data center SolrCloud because every write will have to go to all the nodes across the data center. Right? You have to implement your own disaster recovery. What we did was we have 2 separate SolrClouds being fed by 2 separate entire pipeline, which is Kafka, consumers, SolrCloud, Zookeeper, independent. And that event-based updater is posting to both Kafka. So we did, now we're across the data centers, we are getting event consistency. Document counts will be slightly out of date. One gets the update, a second later the other guy gets update. So we actually monitor for that threshold, tolerance threshold. How many which we will every minute will take the most recent sample, and then find the same documents in the other cloud and compare them, see how far they're off, and we'll keep them under a tolerance threshold. Metrics monitoring. These metrics and lots of metrics are published by SolrCloud via the campaigns, and we pull them out and put into Graphite servers, and we create those nice graphs. There are lots and lots of metrics. It's really good and helpful. So this was real query performance. Here, this was before this point we were sending some random queries, but at this point we turned on our use cases for going to this particular SolrCloud. You see the 500 request rate per second went up. At this point, the document cache hit ratio stabilized at around 45%. This is real. And then, of course, the 95th percentile request time dropped because previously these were fake queries. We were experimenting. And this is traffic going down. This specific time, 9 p.m., people go to bed and come back online. So this goes, it is very common graph across most e-commerce sites. This is the write performance. Here, this is what we are monitoring, the cloud diff and clouds count, doc count diff. So you see some documents come in and these two different colors go out of balance, and one has more number of documents than the other. They come back to zero. You want to keep them at zero. Sometimes you'll have this spike where maybe there's some bottleneck on one of the pipelines, but eventually, as long as it goes back to zero, it's only 2.5 documents for each count diff. So here is the interesting part. Like I was mentioning, it's a CP model, so essentially the leader sends out the write to everybody, all the other replicas. So what you get is the leader is the slowest guy, and all the replicas are fast. They're coming back really fast, but the leader has to wait for everybody and then respond back. So this is the blue line is the leader, and this is the request rate. See, this blue line is the real request rate because it can serve a lot fewer request updates than the replicas. And this is the other collocation. So these are two. This is one data set. This is another data set. Very almost symmetric. So this is our real customer result. The day we turned them on from the left-hand side of the picture, the immediately consistent data store going to resource tiers to Solr. The response time is not spiky anymore, and it went down to about half of what they were getting before. So this clearly shows the benefit. That's pretty much what I had to show, and I'll open it up for Q&A questions.
Do you share your Zookeeper cluster with among Kafka and the SolrCloud?
The question is, do we share our Zookeeper cluster with other things like Kafka uses Zookeeper? Do we share? The answer is no. We keep them separate, dedicated Zookeeper ensembles. We just don't want to. Well, first off, our Kafka cluster is maintained and operated by a different organization, different team. We love them. And they do a really good job. We created that. We did not want to put our Solr on their Zookeeper, and then no, it's VMs. Zookeeper nodes do not have to be very big. They're tiny. Small size or medium size we're using. Just get 5 of them, spin it up. It doesn't need any maintenance, so it's pretty easy. Yeah.
Which application server did you find the best for using the best SolrCloud?
So SolrCloud ships with Jetty, and we actually did not go with Jetty because our infrastructure has more experience in support and operations, and everyone is used to using Tomcat. So we went with Tomcat right now. So, sorry, the question was, what web server are you using? And we chose to go with Tomcat because we had more internal support for it.
Just a follow-up to that question. So if you are using Tomcat, object tuning or threading based on the number of physical cores available from the CPU?
Yeah, those question is, how do we tune the number of threads on Tomcat based on number of cores? So it was more around performance testing, math, starting with a rule of thumb math. How deep do we want the thread depth to be? What kind of query speeds we are expecting? And then putting more load and putting that kind of load into it, and then setting the numbers. And we also have professional help who have experience with SolrCloud and Tomcat. So we did consult experts to get to those numbers. Yes.
So this is pretty much a search engine with some update on the back, right?
Yeah.
And the second question, you say you synchronize the data in the fault tolerance search engines by using Kafka, right? So how do you make sure that the indexes are in sync, right? The fault tolerance and
That's right. So the first question is, it's a search engine with.
so pretty much my understanding is what you presented here was like a search engine operated on the back of Sundays, right?
Correct.
And this is the fault tolerance version, which is a bit of the Kafka, right? So the first question is, how do you keep them in sync, right? And the second, do you have some structured data, or is it flat search? So do you have, for example, hierarchical search, categorization and stuff, or is it flat?
Yeah. So the question was, it's a search engine getting data in by a feeder. Yes, that is correct. And the second question is, how do we keep the two data centers in sync? So the answer is, we don't really keep them in sync. What we do is we monitor the thresholds. As a threshold, if they don't balance out over time, then that indicates a problem, that there might be a problem in the processor or the pipeline or Kafka, something's getting blocked. So the feeders have failures. So if it's failing before posting to Kafka, then it'll write to a local store. If it makes it into Kafka, but the processors haven't picked up, we can look at the lag in the Kafka message processing. We'll look at, oh, this data center is lagging much more behind. We have graphs for that as well. This particular data center is lagging much more behind. Something's wrong, so maybe two of the consumers died. So we'll restart them and it'll process them and it'll get back in sync. If the difference between the two data centers go off the threshold, we'll actually turn off traffic to that data center and go with the most recent one until we bring that other one back up to sync.
How about the hierarchical data search? So is the search you provide to Solar flat search, or you
yes. So the question is, the search actually, how is the schema? Is that flat or hierarchy? The schema actually in Solar, it is flat. There's no way around it. What we have done is we have provided the application to write the custom code to the feeder consumer, so they can pull out attributes from their own object. They know what the object is and what's important. They can go deep inside the object, pull out the specific attribute that they need searched by, pull it up at the top level, and denormalize that thing. The other thing that we have done is actually, since we are essentially using it as a document store, as a cache, we have the entire serialized object. Many of you will cringe at this, but hear me out. We have taken the entire object, serialized it, and stored it as text. We know we are going to hit a wall. It's the size of the index grows because if you store the entire serialized object, but our objects are small enough that we can survive a little bit. Until we get to the point where the application team has figured out that, oh, we only mostly need about 100 fields, and I have logic to pull out those 100 fields from that object, put it up at the flag level, that I don't really need to store that entire serialized object. So that will come in later. But initially to start with, we have a couple of fields in the top, which are the being queried by, and we have the entire object that the orchestration layer was used to. So we we pretty much had very, very minor code change on the orchestration layer. Orchestration layer had code to call these resource tiers, create the aggregate object. What we did, we took the aggregate object, serialized it, and put the whole blob in there. So when it makes the query to Solr, it gets the exact blob, it doesn't know where it got it from. So all of the code got reused, and our development cycle was much, much smaller. So the time to production was much faster. And then we know that our index size will grow, but then we have things like sharding in our toolkit. We have shards, so you can get more shards and so on. So, yeah.
My question is there any potential data loss in the data pipeline? Any part of it, maybe Kafka or Solr itself? Any potential data loss?
So the question is, are there any potential data loss points? And the short answer is yes. In a distributed system with lots of moving pieces, everywhere you have a chance of data loss. So in this simplistic picture, almost everything here, the consumers have retry queues. So if it fails to post to Solr, we'll send it back to a retry queue in Kafka. If this guy can't post to Kafka because Kafka rarely, it can go down and rarely, but still can go down, it does put it into a local store. So every one of them are prepared to handle failures. And like you mentioned, if this guy is on one data center is backed up because that guy's Solr went down or something else happened, these crashed, those messages are living in Kafka. It'll replay. We trigger a replay. Also, what we have is we can process all of if this was running fine, we'll take all of that data, run it back into Kafka, everything will come back here. And our updates are idempotent, so we can run the same update multiple times. Idempotent with optimistic concurrency. In Solr, you have the optimistic concurrency with the merge field. We take care of that so that we can send the same update multiple times and it will still be fine.
So did you evaluate the Elasticsearch? Why do you choose like SolrCloud over Elasticsearch? Because you just mentioned that using Elasticsearch, you may not have the pain point of like blocking the object, something like that.
Yes. So the question is, why didn't we choose Elasticsearch? The question, you'll find many comparisons between SolrCloud and versus Elasticsearch. If you go online and try to look for it, everyone will tell you that here are the differences, make your own choice. No one will give you a straight answer. Our straight answer is we picked it for multiple, mostly non-technical reasons. I mean, both sides have pros and cons technically, but we were doing this for the first time here on this platform in a very short period of time, and we were running with some constraints. Solr was started in 2004, and it's been almost 10 years. The community is much larger. Much more companies, big companies, have been using Solr in production for a long time. There are lots and lots of vendors to choose from who we can get support from, and the talent pool is also bigger. So these were our driving factors. Elasticsearch, I've personally been into Elasticsearch training. We use Elasticsearch in various other use cases internally. So we know it's out there. We are keeping an eye on it. We are going to try it very soon to see to do performance tests, how it runs on virtualized computes. Elasticsearch was built from the ground up to run on distributed virtualized environments. So we are going to evaluate that and bring it in. Some of our customers, clients internally, they might prefer Elasticsearch. So we want to still be able to give them this eventually consistent pipeline and have, instead of SolrCloud, this consumer can be writing to Elasticsearch. So and this pipe design would still work. So yeah, it was and Elasticsearch compared to SolrCloud hasn't been around that long. The community is yet to grow. It's very promising, and so we are. And then Couchbase has Elasticsearch plugin, and so we'll evaluate Couchbase with Elasticsearch. And so yeah, it's not out of the books.
Yeah, I would imagine you do a lot of update on your Solr cluster. So how do you optimize the index over time? Do you have any special strategy to
Index merges?
delete the insert, right? Your index got fragmented. over
Index
time.
merges.
Yeah.
Right. So those parameters, we are tuning that with our Solr experts support that we have. So we tune those based on how many updates we're getting, and they are set at certain recommended numbers, and we put them in, and they're working fine for us. So we do have additional support from Solr vendor.
Seems like you only have incremental updating for SolrCloud. I'm wondering, do you have any way that you could rebuild the Solr index from the?
Actually, currently we are not doing incremental updates. All of our writes coming from here are full documents, so we post the entire document.
Yeah, but in terms of the whole corpus, not just.
Yes, we can do that. We can rebuild the entire index from Hadoop right here. We can put it back here in a matter of minutes. We can rebuild the entire index.
Are you doing that? I mean,
We've done it quite a few times before going to production. And so one thing we do in production is if we have new fields, something you have to index to a new collection, we're running with Solr aliases. We index the whole thing into a new collection and then do an atomic alias swap.
so my question is, when you rebuild a whole index on Hadoop, and there's some updating on SolrCloud, how would you?
Right. So there are two ways to do index into SolrCloud. You can create the index file and send them to Hadoop in the directory, or you can send it here, or you can send the updates to SolrCloud. We are not directly pounding SolrCloud with Hadoop reducers. We're sending the reducers, send the data to Kafka. That flows in through here. There's batching up every second, so we have that additional layer of protection to not kill SolrCloud. So we do batch updates.
So how big the index size and how do you avoid the garbage connection in general?
The question is, how big is the index, and how do we avoid garbage collection? There are two separate questions. So how big the index is something that I cannot disclose. But garbage collection settings were, like I showed before, based on our size of the machines, how much we can give and how much we tuned the GC settings. And the GC, these settings, there are some of these sets are available on the forums, on the Solr forums. But we talked to the other internal team we have, which uses Solr. We asked them for their settings, and they were completely different from what we were going towards. Couldn't use them. So I would caution you from lifting someone else's setting and completely relying that this is going to work. So you have to take a baseline and then start tuning it. So we got professional help for tuning these to have a smoother garbage collection, you're going to get a sawtooth regardless of what you use, right? But you want a smoother sawtooth. So we have 6 gigs of JVM, and then it goes much smoother. It doesn't do, you don't get a huge amount of JVM memory, and then your GC pause goes for 30 seconds or a large number of seconds. Your search engine is unresponsive. And imagine if you start all of your machines at the same time and all of them go up and then all of them crash at the same time, your search size will be down. So those are all the realities to face.
How many live products are you handling with this?
I'm not sure I can disclose that number. The total catalog size, that's not public information, right? Yeah. But it's in many millions. And and growing.
You guys are hosting third-party inventory now, right?
We are also, yes. So there's a project which essentially pulls lots and lots of products into the catalog, and we have third-party sellers. So catalog is growing every week, every month. It's, I would say, 6 times than a year and a half ago. 6 times of whatever number that was. Sorry, I couldn't answer your questions. That's straightforward. Any other questions?
Just one more.
Sure.
Let's assume that you've got a single collection, and every one of your sites or like that is. On an average, how many first level shots do you really pick up?
So based on our data size and the size of the machines we had, they're large memory, large SSDs. We didn't really need to shard, but in order to prepare for shards and shard splitting, we actually started with 2 shards. And with 2 shards, there's plenty of room. And what we did was we have oversharding, so the other shard is also on the same machine. So each machine is running 2 shards, and we did that for multiple reasons, for experiencing sharding, shard splitting, as well as trying to get more threads of the cores working to get the query, so better utilization of CPU and threads.
Did you also figure out a way to name those shards in a more user-friendly manner instead of just calling them some weird number?
No. The question was, did we figure out any naming convention for shards? The answer is no. It's better to not worry too much about things that should not be that important up front. All right, if there are no more questions, thank you. Thank you for your participation.